right? The last thing we want to do is something that's going to be super important for the rest of the semester, and that's strengthening, right? Because most of the time, right, why is strengthening so important to physical metallurgists? Right? Structure, right? Do we design for yield? Do we design for yield strength or ultimate tensile strength? Yield, right? You don't want your structures plastically flowing while you use them, right? You want them to not yield. So generally, we are trying to push the yield strength as high as possible while also maintaining some ductility, right? So when we talk about aluminum alloys the week after next, we're going to start with precipitation strength in alloys and also solid solution strengthened alloys, right? We'll talk about two different classes, right? Based on the alloying elements that are put in, giving you different strengthening mechanisms, right? We'll talk a lot about why aluminum doesn't work harden as well as other systems, right? Strengthening is a super important topic that's going to keep coming up over and over and over again repeatedly throughout the rest of the semester, right? So if we look at hold on one second. I couldn't hear myself think. Okay, so most of us are not used to looking at the stress-strain curve for a single crystal, right? Usually when we do a stress-strain test, it's on a polycrystal, right? So think of this just sort of schematically. But if we have a single crystal, the stress-strain curve looks a little strange. We first go through a elastic region, a yield, followed by what's called easy glide, where we have very little resistance to slip. Stage 2 hardening, where we have a rapid degree of work hardening. And then stage 3, right, where we have a decreasing hardening rate. And we'll talk about this a couple times throughout the next week or so. But basically, what's going on between stage 1 and stage 2? Right? Why is there a change? Dislocations are increasing and interacting, right? Okay, so if we have that, dislocation interaction, right? That's the key idea behind all of strengthening, right? Dislocations are the primary carrier for plasticity in a metal, right? There's also twins. There's also, depending, you can have stress-induced martensitic transformations and things like that. But for the most part, we're really interested in dislocation motion. So how do we make metals stronger? We want to impede dislocation motion, right? How can we impede dislocation motion? Well, here we said we can do it by putting in more dislocations, right? So the dislocations interact. What other things can we do? What's that? I'm hearing a couple things, but none of them are quite loud enough. So precipitates, right? We can put in secondary phases, right? We can put in grain boundaries. Grain boundaries interact. And then there's only one more thing. We only have one more choice. Solid solution, right? Solute atoms, other atoms to get in the way, right? which means basically strain, right? So that's it. Those are the only four things, the only four knobs we have to turn. We can put in elements to do solid solution strengthening. We can put in elements to cause secondary phases. We can change the grain structure, or we can beat the hell out of it. That's it, right? That's all of strengthening in a nutshell. Right, now we got to get into some of the details of it, right? So just as a review, remember deformation occurs on slip planes along slip directions, right? We don't deform across arbitrary planes, and everyone remembers the Schmidt law, right? How we resolve our shear stress, we project our stress onto the plane, and then onto the direction. In FCC, our slip systems happen to be, what are they? Everyone knows this. What planes? 111, what directions? 110, why is it 111, 110? Close packed plane, close packed direction. Perfect, right? Okay. Why does it prefer to be on the close packed planes? Furthest apart. Why in the close packed direction? Shortest Berger's vector on that plane, right? So the farther apart the planes are, the easier they are to slide past each other. The close packed direction, because we have the shortest Berger's vector in that plane. BCC, well, so for FCC, we only have one slip system. You can get at really high strain rates and really high temperatures sometimes, like shock waves. You can get cube slip, right, where you slip on the 100 faces along the body, the diagonals, right, the 111 close packed directions. Really a rare thing. You got to really hammer it hard to get that to happen. What about BCC? We have a whole bunch of different slip modes, right? We don't have close packed planes in BCC, but we do have close packed direction, right? Which is the 111 direction, right? So for you welding students, you have to take a quick look at your unit cells, right? It's not hard, I promise. Right? So, but there are a couple different options for planes that contain the 111 direction, right? And so which of these is going to be active? You've got a whole bunch of choices, right? So it's all going to depend on the actual temperature, the loading condition, right? You can operate a whole bunch of these. So there's a notion of slip in BCC is sometimes called pencil glide. You might have heard this, right? You can imagine a bunch of pencils put together in a bunch, right? And if you think about how you can slide them, right? If you have pencils packed and then you shear them this way, right? There's an infinite number of planes I can shear them. Right, maybe I'll do this. Maybe I'll bring in some pencils, right? So essentially, there's a whole lot more degrees of freedom, right? So we have 48 potential slip systems that we need to think about in BCC, and the energy difference between them isn't nearly as great as it is in, say, HCP, right? What's our close packed planes in HCP? Right, our basal planes. What's our close packed directions? Right. The prismatic directions, right? So we have two systems, two families, right? We can have basal slip or prismatic slip, which are both along the close packed directions, right? Slip on the prism plane in the close packed direction. What's the problem with those two modes? What's the Schmidt factor for C-axis? If I have a load directly along the C-axis of my crystal, do I have any driving force to activate either basal or prismatic slip? No, right? Because my force is orthogonal to my Berger's vector both times, right? So I'm not going to be pushing that way. I have no shear stress. So that means I can't activate either of these from C-axis tension or compression. So I have to activate much less favorable, less close-packed, either pyramidal A or pyramidal C plus A, right? Why do I call them pyramidal A and pyramidal C plus A? Well, pyramidal A is parallel to the A direction, one of the prismatic direction, but it's on a pyramidal plane. Pyramidal C plus A, I have my Berger's vector has both a and a C component, right? It's not just pure A, right? So compared to BCC or FCC, there's a lot more anisotropy. It's much more difficult to activate C plus A slip than it is to activate any of the A systems, right? So it takes a lot more force, or I need a much higher temperature, right? I also have a much smaller number of systems, generally, okay? When we get to magnesium and titanium, we'll talk more about this, because sometimes, for example, magnesium basal is very easy, but in titanium, basal is hard and prismatic is easy. And we'll talk about why that comes about when we have these systems. Yeah.
What do you call the loss?
There's higher order C plus A. There's multiple pyramidal C plus A systems. They all just sort of get lumped together, and generally they are not both active. For example, again, in magnesium and titanium, you have different C plus A systems that tend to operate. Okay, so if we go back to what you learned from the seniors, from Professor Anderson in the mechanical behavior course, right? You talked about the Schmidt law. You probably also talked about it in the Callister, the 2010 course, I would hope, right? A little bit. Right. So Schmidt made some observations for single crystals and said that initial yield varies from sample to sample depending on the position of the crystal lattice relative to the loading axis. And he said that it's the stress resolved along the slip direction on the slip plane that initiates plastic deformation. And that yield happens when you reach some critical value called the critically resolved shear stress, right? That's independent of the tensile stress or other normal stress on that lattice plane, right? So really all we care about is shear, right? Will a metal ever yield under a pure hydrostatic pressure? Right? If I take a hunk of steel and put it at the bottom of the ocean, or put it in a pressure chamber, keep increasing the pressure on it, will you get yield? Right? No, right? Because a perfectly hydrostatic stress state, there's no shear in any direction, right? So you may have seen this; it'll come up in the reading, but single crystals, right? If I cause slip here on this plane, and I have this set top sliding relative to this, I introduce a moment, right? So that leaves me a rotation of my samples, right? Because we think about keeping in a tensile test, these grips are fixed, right? So the only way we can get this sliding, right, without the grips offsetting is to also introduce a bending, a rotation of the lattice. And under tension, the slip direction rotates towards this tensile axis. And it's not hard to convince yourself that this has to be the case if you play with it for a couple minutes. Under compression, the slip plane normal is going to rotate towards the compression axis, the opposite. The sense of rotation is going to be is going to be opposite. Okay, so that's sort of macroscopic stuff, right? For the last 10 minutes, we'll think about what happens on the dislocation level, right? And for a lot of you, this is a review. I apologize, but for a fair number of you, it might be the first time you've ever really looked at this, right? We said that strengthening occurs by impeding dislocation motion, right? But that assumes that the dislocation is mobile to start with, right? So first we have to think of what's the force required to move a dislocation, right? Do ionic ceramics have dislocations in them? Right? Do polymer crystals have dislocations in them? I would hope you'd think that if by asking the question, I'm leading you to the answer of yes, right? But why aren't ceramics, right? Diamond has dislocations in it, right? Why isn't diamond ductile? Right? So dislocations aren't mobile. Why aren't they mobile? What's different between diamond or rock salt or metal? What? The bonds, right? So in diamond we have covalent bonds, right? Not easy to break, right? In rock salt we have the complication, we have ionic bonds, but then we also have the fact that dislocations have a charge associated with them because they're associated with point defects of the lattice, right? So in both of those systems, the dislocations are not mobile until you get to a high enough temperature. For diamond, that's like after the temperature turns back to graphite, so you don't need to worry about that. Right? For ionic crystals, a lot of the original dislocation work to measure dislocation velocity was actually done in rock salt or other halides, calcium fluoride. Right? They were compressed underwater to keep them from fracturing, right? At relatively high temperatures. Then you could take them out and do etching and look at how the dislocations have moved under a certain given load and calculate dislocation velocities that way before the electron microscope was ever built. Right? So we have to calculate, before we think about how do we get things in the way of dislocations, we have to think about how hard it is for a dislocation to move in the first place, right? Dislocations don't move by themselves, right? We need a force on them to get them to go, right? And with that, the intrinsic lattice friction, we call that the Peirels-Navarro force, right? So it was originally developed by Peirels in 1940 and then independently redone by Navarro in 1947. Right, and it's a direct consequences of the distortions in the lattice caused by the presence of the dislocation. Right? How disruptive is the dislocation to the structure? The dislocation doesn't cause a large disruption. It's probably easy to move, but it probably doesn't accommodate a lot of slip by moving. Right? Okay. So if we think about the physical basis for the Peirels stress. We start with a edge dislocation here, and we move it along. We have to pass through this high energy configuration where we've moved our extra half planes of atoms to the worst possible place they could be, and then once we're past that, they're going to snap over, right? So essentially we have to this is the energy hump that we have to overcome, right? Right. So we have to think about the distortional field caused by this. And we can parameterize this by what we call the width of the dislocation core, right? What do I mean by the width of the core? Well, we look at how much individual atoms are displaced from the position they want to be due to the presence of that dislocation, right? So dislocations above the slip plane here, are these in tension or compression? Are they closer or farther apart than they want to be? What? There's an extra plane jammed in there. So they're closer, right? Right? There's more people smashed in. Down here, these are farther apart than they want to be, right? So they have a, right? They're feeling pulled, right? So they have a tensile. Okay? So, but we look at this displacement, right? And basically, arbitrarily, we sort of say when that displacement is 1/4 of the Berger's vector, and when it falls to that level, that's what we call the dislocation core width, right? And it tends to be about between 1 and 5 Berger's vectors, right? And so remember when we did some integration for the stress field and the energies of a dislocation, and we picked that W naught, and we said we're going to stand off and integrate away because once we get to the core, our displacements become infinite and everything goes to hell, right? Essentially, we're going to pick a value that's between 1 Berger's vector and 5 Berger's vector, dependent on the system, for that R naught, value. Okay? So if we look at widths, if we have a nice close packed structure or a nice metal, right, we have wider dislocations. Our dislocation core is delocalized. It's more spread out. Whereas if we have non-close packed structures, the width is smaller and our distortion is concentrated in a smaller area, right? For FCC, right, we tend to have very wide dislocations and small Peirels stress, right? We also have very little yield strength dependence on the temperature, right? The narrower we make it, the larger our Peirels stress is, the harder it is to move, right? The more concentrated our distortion that we're moving through the lattice. So covalent ceramics like diamond have very narrow dislocation cores, very narrow widths, very large Peirels stress. The narrower the core, the more the temperature dependence of the yield is, right? So we can make observations that the core in a basal dislocation in HCP is going to be much more distributed than in a C+A type dislocation, right? And these are things we can actually now see with high resolution TEM, right? You can actually see some of these distortions, which I think is pretty dang cool. We can also calculate them, which I also think is pretty cool. Okay, so that's where we'll stop. We'll get to the explicit form of the Peirels stress. We'll finish this up Wednesday and Friday, and then Wednesday of next week start with aluminum alloy systems.